How AI actually predicts every word it says, blue, or clear, or cloudy. That's not a typo. That's literally how an AI decides what to say next. If I type the skies into ChatGPT, Gemini, or Claude, the model isn't thinking about the sky. It's running a calculation, assigning odds to every possible next word, then picking one. Blue gets a high score. Purple gets a low one. Sandwich gets almost none. That's the entire trick behind every AI chatbot you've ever used. Today I'm breaking down exactly how it works. No jargon you can't follow. No math you need a degree for. Just the real mechanism. Let's start with the name, because it's more literal than people expect. Large, because these models have billions of internal settings called parameters tuned during training. Language, because they're built specifically to work with text, words, sentences, code, conversations. Model, because it's not a database. It's not looking anything up. It's a mathematical model that estimates probabilities. Here's the one sentence that unlocks everything else in this video. An LLM is a system trained to predict the next word in a sequence over and over, based on everything that came before it. That's it. Questions, essays, code, jokes, all of it comes out of that one unrepeated action, done fast enough and well enough that it looks like understanding. So how does a machine predict the next word well enough to write an essay? Step 1. Your text gets broken into pieces called tokens. Sometimes whole words, sometimes word fragments. Step 2. Each token gets converted into a list of numbers called an embedding. This is where it gets interesting. These numbers aren't random. Words that mean similar things end up with similar numbers. Dog and puppy sit close together in this numerical space. Dog and spreadsheet don't. Step 3. Those numbers flow through something called a transformer. The architecture almost every modern AI model is built on. Inside the transformer is a mechanism called self-attention, and this is the real breakthrough. Self-attention lets the model look at every word in your sentence simultaneously and decide which ones actually matter for predicting what comes next. Take the sentence, "The trophy didn't fit in the suitcase because it was too big." What does it refer to? The trophy or the suitcase? A human just knows. Self-attention is the mechanism that lets the model weigh trophy more heavily than suitcase when predicting what it means, based on context. That's the architecture. Tokens in, attention across everything, prediction out. None of this works without training, and training happens in stages. Stage 1, data collection. Engineers gather enormous amounts of text, books, websites, articles, code repositories, sometimes conversations. We're talking a meaningful fraction of the internet. Stage 2, pre-training. This is the core of it. The model gets shown real text with pieces hidden, and its only job is to guess the missing piece. Every time it guesses wrong, an algorithm called backpropagation nudges its internal parameters slightly, so next time it's a little more accurate. Now, do that correction billions and billions of times across a huge chunk of human writing, and something strange happens. The model doesn't just learn the sky is blue. It starts absorbing grammar, factual patterns, reasoning structures, writing styles, all as a side effect of getting better at one narrow task. Guess the next word. Stage 3, fine-tuning. After that broad training, the model gets trained again on a smaller, curated dataset, often with real humans, rating its answers, teaching it to follow instructions and avoid harmful or useless responses. This is the stage that turns a raw text predictor into something that behaves like a helpful assistant. Stage 4, evaluation, and deployment. Before release, the model gets tested for accuracy and safety, then shipped into the apps you actually use, usually with extra safety layers on top. Let's make this concrete. Say you type, "Explain photosynthesis simply." Your sentence is broken into tokens. Each token becomes a numerical embedding. Self-attention scans the whole sentence and flags the key concepts. Photosynthesis, explain, simply. The model computes a probability distribution over every possible next token. Thousands of candidates, each with a score. It selects one, sometimes the top scoring one, sometimes with a bit of controlled randomness, so answers don't feel robotic and repetitive. That new token gets added to the sequence, and the entire process repeats, now predicting the next token with the one it just wrote included as context. Word by word, that's how you ended up with a full explanation. It's not writing the whole answer in one shot in its head. It's building it one probability calculation at a time, thousands of times, faster than you can read. Here's why this matters beyond trivia. Because LMS learn abstract patterns rather than memorizing fixed answers. They generalize well. Ask a question no one has ever typed before, and they can still often produce something coherent and useful. That's the power of pattern learning over lookup. But that same mechanism is the source of their biggest weakness. The model isn't checking a database of facts. It's predicting what sounds statistically right, which means it can produce completely confident, fluent, well-structured sentences that are just wrong. That's what people call a hallucination. And it's not a bug that gets patched out easily. It's a direct consequence of how the whole system fundamentally works. It also means these models don't have real-time knowledge of the world unless they're explicitly connected to search tools or updated data, because everything they know was frozen in at training time. Once you understand that distinction, predicting versus knowing, you read every AI answer differently. You start double-checking specific facts instead of trusting the confident tone. That one mental shift will save you from more AI mistakes than any tool or setting ever will. So next time you type into ChatGPT, Claude, or Gemini, remember what's actually happening under the hood. Tokens becoming numbers, attention scanning for relevance, and one probability calculation after another. String enough of them together, and you get language that feels like thought. It's not magic, it's math, at a scale that's hard to picture. And now you actually know how it works. If you want the next layer down, how these models get trained specifically to follow instructions, or how tools like search and memory get bolted onto them, that's exactly what I'm covering next. Subscribe so you don't miss it.